Okay, now we are just going to work out a few more examples in Bernoulli. Point out that I consider we are at somewhat the same place we were in dynamics when we had the kinematics in place and we had our first physical law, F equals ma. Here the physical law is simply Bernoulli, but once that's set up, you run out some examples. Last time we did the pitot tube, which is not only a good example, but one of the main ways, or one of the simplest ways, of measuring velocity. So this time, the first example is a free jet. This example has some history to it. Google Torricelli. See what you get. Also check out that video, 3.9 in the book. Pretty good. Now the free jet is pretty simple. Look at points 1 and point 2 here. What we're doing is going from point 1 to point 2 along a streamline. Now, which streamline that is, you don't care. There's some streamline. You don't need to know which streamline, which is part of what makes this a useful tool. You had to know that, suddenly it would be much more difficult. You don't. You just need to know there's a typical streamline. Now, note that I'm taking it between 1 and 2. 2 is still within the enclosure. Now, 0.5, odd numbering, 0.5, what's going to happen down there, the velocity, is you've got free fall. So by the time you get from 2 to 5, the thing will have fallen through height h. It will have accelerated, be going faster. But our objective here is to look at the fluid flow while it's still constrained, and we can write Bernoulli's equation from 1 to 2. For the free jet example, we're dealing with a simplest case, and at point 1, the idea is that area is very large compared to the area down at 2, so that you're going to ignore the fact that point 1 really is slowly coming down. We're just going to let that be so big that, in other words, the area that is encompassed by that free surface at 1, that we can say essentially the drainage rate is negligible. In a bit, we're going to tweak that, but right now, that's where we are. And I'll make a few, well, here is, I'm sorry, just take Bernoulli's equation from 1 to 2, write it, and you'll get this. So the free jet is very like Bernoulli, I'm sorry, is very like the pitot tube in that you've got the velocity proportional to the square root of some driver. There is pressure gradient. Here, it's height, or gravitational force. So you unsurprisingly get similar equations. Now, two more features of this free jet situation. One is this, a fairly small point, but a significant one sometimes. That is, if you let that outlet, D, from 1 to 3 be large enough, well, then you can get some variation across the jet. Notice, by the way, here that we've turned the jet around horizontally. Okay, so that the various from 1 to 3, you're at a different depth, h. But if D is small compared to h, then you can assume it's pretty much constant along that. However, so there, the fact of 1,3 being finite is not really important in general. This one's a little more important, especially in that you might miss it. It's not obvious instantly this is going to be going on. But when you look at it, it's not surprising. Look at points 1 and 3 now. This is called the vena contracta effect. I have no idea if my Latin's even close on that. Now, at points 1 and 3, up from 1, down from 3, you imagine a flow, a streamline, right going along that wall. I mean, just skimming it, okay? And as it gets to 3, well, it's not going to turn a right angle turn. That would require bringing it through an abrupt right angle, which means raise a curvature of 0, which means infinite acceleration, right? Because accelerating a fluid is can be either changing its velocity or its direction. Here we're doing a 90-degree direction change, and that's going to be gradual. So the point is that at 1 and 3, by the time it executes that turn, we've necked the flow down some. And so dH may be the actual area of the hole in the side of your container, but dJ is going to be the diameter of the jet once it steadies out. And take it as just simply an empirical given that once you come a little distance away, it will be, for our purposes, constant across that stream. Remember, our purposes being, let me say a sidebar here, this is an exploration of Bernoulli's equation. We're going to be spending the next couple of months, or next month at least, setting up the full fluid equations. What we're doing now is taking historically a very useful example, a very important example, and one that lays the basis for where we'll go later. Okay, now back to where we are. The continuity equation. There is one additional equation that you'll see in fluids for which there's no analog in dynamics. In dynamics, we had a particle. Okay, it didn't gain weight, it didn't lose weight. It just had mass m, and along it went. Now in fluids, you had to drop that because you have a continuum. Therefore, rather than a mass point m, we've got a small volume and a density. Okay, so the mass is that small volume times the density. That gives you a small mass. And for the continuum, that becomes essentially a constant because it's small enough. Back to the Newton number in my first lecture. However, keeping track of that is going to require the introduction of a new equation, the continuity equation. Now at this point, continuity equation is very simple. In fact, let me back up here and show you how you get it, quite simply. Let's look at where the jet is leaving from 1 to 3, okay, where you've got a, call it diameter DH, got a hole there, let's say, and downstream, it comes out, and once you've got the flow going steady, how do I say it, once you've turned at 90-degree angle and you're heading out, you've got a smaller cross-section that's moving faster. Well, you know that the amount of fluid coming out at diameter dH is equal to the rate of fluid crossing the diameter dJ. Well, the area at dH is going to be what? It's going to be pi dH over 2 squared, that area. Downstream is going to be pi dJ over 2 squared, that area. So the area at the beginning times that velocity equals the area downstream times that velocity. Remember that. Quite simple. And two more terminology points here before I move on. AV is the volume flow rate. Just forgot the dimensions. Dimensions of A, dimensions of V. You're going to get cubic. You're going to get cubic L, or you're going to get L cubed per T. And if you multiply that times rho, you're going to get a mass flow rate. We'll be using those. Now, on to another variant. As I said before, we're taking the free jet and we're saying, okay, look, let's pour some Q in here and keep that thing steady. In other words, we're not going to allow the thing to slowly drain out. We're going to make it steady. Well, no particular challenge. And I can tell you right now, if you think about it, what do you think you're going to do? You're simply going to add in, which had in the free jet, the condition that the flow rate coming in equals the flow rate out. That's it. There's nothing up my sleeve. That's it. There's just one more relationship, that continuity equation. So it's a simple step, but one that down the line you'll see in retrospect was the introduction of something that would take on sort of a life of its own. In the next chapter, in fact, you start to see that this continuity equation and just sort of the kinematics of the flow, yeah, not so easy. Right now, they're pretty easy. And finally, there are 3 more flow meters that you can use Bernoulli's equation for. This slide shows you a Venturi meter, and you can see the strategies in that bottom especially. The Venturi meter, what you're doing is you're taking a flow at 1 and you're speeding it up and measuring it at 2. One thing you could certainly do is if you had a large flow, you could bleed off some water and bring it down to a smaller a smaller area like a 2 and take your measurement there. But the measurement there is just you apply Bernoulli at 1 and 2 and you figure it out. Now, upping our game a little bit, by which I mean the size and what we're talking about here. The example that seems to be universal when people talk about sluice gates is flow in an irrigation ditch. Okay, so now we're talking about larger scale things here. And what you do is you take that sluice gate, you've got a flow at the left here on your diagram, which is figure 3.19. You've got some flow, presumably not moving too steadily, or I'm sorry, not moving too quickly, but at some significant depth, Z1, and you'd like to know what that is. Well, the flow itself is pretty slow. You could measure the velocity straight away, but it's not so easy to do. A slow velocity, measure a long time. Well, a good way to get a quick measure of what that velocity is raise the gate. Okay, look down here, you see a vena contracta, all right? Water jet comes out there, goes to a velocity V2, and again, using a combination of Bernoulli and continuity of flow, you can solve for V2. Third option, a little more complicated. Let's suppose you, for some reason, just can't get at the bottom of this fluid. One reason or another, it's not really accessible. But what you can do now is rather than open the plate at the bottom, you're going to open the plate at the top. Okay? And what you're going to do is, as before, follow a streamline. I mean, here's the Bernoulli application that you're seeing time and again. Here, now, the streamline is the one from 1 to 2. So you're simply going to follow Bernoulli along that and apply whatever you need. And now in this case, as you can see from the drawing, it's not quite as simple as the sluice gate. You get the thing coming down, you don't have to worry about it falling, accelerating, but still, if you do it clearly close to where that opening is, you won't worry about acceleration due to falling too much. But it's a little more complicated. However, still, having Bernoulli useful in this case is worth a lot. It's a very simple relationship. You follow the streamline, you get the answer. In fact, if you remember from the very first paragraph, almost this chapter, Munson said that, what was it? Bernoulli was one of the most used and abused equations in fluid mechanics. And the reason is that once you see how to use it, it's so simple. You can use it in situations and get a quick and dirty answer, which sometimes, if you're in control of what's going on, meaning you know the physics, you know where you can apply things, where you can't, you can get a really good, fast answer. So for Bernoulli, go forth and have fun with examples.